A ball, mass 0.4 kilograms, is initially moving to the left at 30 meters per second. After hitting the wall, the ball is moving to the right at 20 meters per second. What is the impulse of the net force on the ball during this collision with the wall?
All right, so direction is important in this chapter for this one. So remember, when I see 30 and 20, it's not just 30 and 20, they have directions. So if in this case, I'm going to say to the left is my negative direction, to the right is my positive direction, and I'll just note that on my work that I've chosen to the right is positive, to the left is negative. In making those choices on direction, we end up adding those because those negative signs cancel, so you get an overall of 20 kilogram meter per second. It does come out positive, which is reminding me that it is to the right.
Correct answer, A, 20 kilogram meter per second to the right. Yes, direction is important. You are testing a new car using crash test dummies. Consider 2 ways to slow the car from 90 kilometers per hour, that's 56 miles per hour, to complete stop. Option 1, you let the car slam into a wall, bringing it to a sudden stop. You let the car plow into a giant tub of gelatin so that it comes to a gradual halt. In which case, is there a greater impulse of the net force of the car?
So number 2 here, don't get confused between impulse and force. Those are different things. So in this case, the impulse is going to equal the mass times the change in velocity. Since both of those cars have the same mass, same change in velocity, they will have the same impulse. What you might have thought of is that if the time is different, they're going to experience different forces, which is true. That's why we want to have things that increase time to decrease force for the same impulse, okay?
Correct answer, yes. Impulse is the same for both. A small car collides head-on with a large SUV. Which of the following statements concerning the collision are correct? There may be more than one correct choice.
All right, it's important to think about Newton's third law here. So they will experience equal and opposite forces because they're pushing on each other for equal amounts of time. We'll see that force times time, they have equal and opposite impulses.
So the correct answer is there. Yes, they have the same magnitude force, and because that occurs over the same time, they have the same change in momentum as well. If the momentum of a single object is 0, the kinetic energy must also be 0.
All right, so if the momentum is going to be 0, that means either mass or velocity has to be 0. So if the object is an object, the velocity has to be 0 in order for momentum to be 0. If my velocity is 0, that means my speed is 0, so my kinetic energy must be 0.
Correct answer is true, yes. Next one. If the momentum of a pair of objects is equal to 0, the kinetic energy of those objects must also be 0.
All right, they brought in 2 objects now. So momentum, will remember direction is important. So if I have the 2 objects moving toward each other, I can have momentum of positive 5 and momentum of negative 5, which gives me a total momentum of 0. But there is motion, so there still is kinetic energy there. So it doesn't have to be 0 kinetic energy if the momentum of the system is 0.
Yeah, that one is false. Direction, again, important here. If the kinetic energy of a pair of objects is equal to 0, the momentum of those objects must also be 0.
All right, they flipped that question around on us. So now kinetic energy is 0. Well, the only way kinetic energy can be 0 is if there's no motion, because that's the energy of motion. And if there's no motion, no speed, there's no velocity for either object. And so yes, the momentum also must be 0.
Correct answer there, true. A 3 kilogram rifle fires a .005 kilogram bullet at a speed of 300 meters per second. Which force is greater in magnitude, the force that the rifle exerts on the bullet or the force that the bullet exerts on the rifle? Correct answer?
All right, this is a third law situation, so the bullet and the gun will have equal and opposite forces as they push off each other. Because they have different masses, they will have different accelerations, they will have different velocities, okay?
Yes, they have the same magnitude, Newton's third law again. A heavy rifle initially at rest fires a light bullet. Which of the following statements about these objects is true if considered in an isolated system?
All All right, so again, we're using Newton's third law here. So Newton's third law says those forces will be opposite and equal for the same amount of time, so they have the same changes in momentum, just in the opposite directions. Now, because they have the same force, if the smaller the mass, the larger the acceleration. So they will experience different sizes of acceleration. Because they have equal and opposite changes in momentum, their momentums will be the same. The smaller one will be moving faster though. Now, when we bring that same idea down to kinetic energy, well, speed is squared. So because I increased speed by the same amount I decreased mass, but it was squared, that actually causes the smaller one to have more kinetic energy.
So yes, they have that same force, and again, same time means same change in momentum. Which of the following statements is true about an inelastic collision?
Okay, so this one's straight off your green sheet. So we look up inelastic, we see they start apart, end apart. Momentum is conserved, meaning if one loses some momentum, the other one has to gain it. So I still have the same total amount of momentum there. And kinetic energy is lost, so kinetic energy is not conserved in that situation.
So yes, using our green sheet, we see momentum is conserved, kinetic energy is not, and so if one loses it, the other one gains it. B and D are the correct answers. Which of the following statements is true for an elastic collision?
Another one off our green sheet. So elastic, start apart, end apart. Momentum is conserved, so if one loses momentum, the other one gains it, so I still have the same total amount of momentum. Kinetic energy is also conserved in this elastic type of problem. So if one loses kinetic energy, the other one gains the same amount, so I still have the same total amount of kinetic energy, so there's no change in that overall kinetic energy.
Again, using our green sheet, we see that both momentum and kinetic energy are conserved, so if one loses momentum, the other one gains it. If one loses kinetic energy, the other one gains it, so it stays constant.